On September 23, 1999, a room full of engineers waited for a signal from Mars. 9 months earlier, NASA had launched a spacecraft called the Mars Climate Orbiter. It had crossed millions of kilometers of empty space, survived the journey, and was now performing the most dangerous part of its mission, firing its main engine to enter orbit around Mars. For a few minutes, the spacecraft passed behind the planet. Losing contact was expected. Then the moment came when the signal should have returned. But nothing. The engineers waited. They searched different frequencies and checked the tracking network, but the spacecraft never spoke again. A mission costing more than $327 million had reached Mars and disappeared because two pieces of software disagreed about how to measure force. But the famous metric versus imperial mistake is only the beginning of the story. Mars Climate Orbiter launched from Cape Canaveral on December 11, 1998, aboard a Delta II rocket. The spacecraft weighed about 629 kilograms and had two major jobs. First, it would become an interplanetary weather satellite. Its instruments would study dust, water vapor, clouds, temperature, and changes on the Martian surface. Scientists hoped the data would help explain how the climate of Mars had evolved and where some of its water might have gone. Second, the orbiter would act as a communications relay for the Mars Polar Lander, another spacecraft scheduled to arrive a few months later. The plan was demanding, but it was not unusual. NASA and the Jet Propulsion Laboratory had already sent successful missions to Mars. During the 9-month cruise, controllers performed 4 trajectory corrections, gradually guiding the orbiter towards its target. From Earth, everything appeared to be working. The spacecraft itself was healthy. Its engine was ready. Its computers were following commands. The problem was that the navigation team did not know exactly where it was. Spacecraft do not travel in perfectly straight lines. Sunlight pushes against them. Gravity from planets and moons changes their course. Even small thruster firings used to control orientation produce tiny changes in velocity. To navigate accurately, engineers must model all of these forces. For Mars Climate Orbiter, a ground program supplied data about the impulse produced by the spacecraft's small thrusters. The navigation software expected that information in Newton seconds, the metric unit required by the interface specification, but the program delivered the values in pound force seconds. 1 pound force is about 4.45 newtons. So when the navigation system read the numbers as metric values, it underestimated the effect of each thruster firing by a factor of roughly 4.45. This was not the spacecraft confusing meters with feet, and it was not an onboard computer suddenly making a bad calculation near Mars. The mismatch existed between two ground-based software systems. One produced a number in one unit. The other accepted the same number while silently assuming a different unit. There was no warning because the number still looked like a perfectly valid number. Each individual error was small, but the thrusters fired repeatedly during the journey. Over time, the difference accumulated, and the predicted trajectory slowly separated from the spacecraft's real trajectory. Mars Climate Orbiter was supposed to pass roughly 140 to 150 kilometers above the Martian surface during its arrival. Instead, later analysis placed its closest approach at approximately 57 kilometers. NASA believed the spacecraft could survive an altitude of about 85 kilometers. Below that, the Martian atmosphere, thin by Earth standards but still dangerous at orbital speed, would create excessive heat and stress. The orbiter flew far below that limit. It may have broken apart and burned in the atmosphere. Another possibility was that it skipped away from Mars into an unknown orbit around the Sun. Either way, the result was the same: no signal and no spacecraft. At first glance, the cause seemed almost absurdly simple. Convert the units and the mission survives. But spacecraft are built with layers of reviews, tests, interface documents, and independent checks precisely because people make simple mistakes. The more important question is not why one person used the wrong unit. It is how that error survived all the way to the Mars. The investigation found that the mismatch had passed through requirements reviews, software walkthroughs, testing, and mission operations without being caught. The interface documentation specified metric units, but the team did not perform an effective end-to-end verification that the software output matched what the navigation system expected. And there were warning signs during the flight. Members of the navigation team noticed inconsistencies in the trajectory. They discussed their concerns among themselves, but the concerns were not communicated clearly through a formal process that forced the issue to be investigated and closed. Communication between the spacecraft team and the navigation team was weak. Some important discussions relied on informal channels. Responsibilities were unclear, and people did not always know who had the authority to make a final decision. The navigation team was also supporting 3 Mars missions at the same time. It was understaffed. Some members lacked deep familiarity with the spacecraft, and the transition from development to operations had disrupted continuity. NASA's later review concluded that management had focused heavily on cost and schedule without giving enough attention to mission risk. In other words, the unit mismatch was not hidden by some impossibly complex technical mystery. It remained hidden because the organization surrounding the software failed to connect the clues. There was even a possible final opportunity to save the mission. The flight plan included a contingency maneuver known as TCM-5. Shortly before Mars orbit insertion, engineers discussed using it to raise the spacecraft's approach altitude, but the maneuver was never executed. The necessary analysis, testing, and procedures were incomplete. The team was not prepared to perform it safely at short notice. Changing the trajectory could also disrupt the tightly planned schedule for aerobraking and support of the Mars Polar Lander. Most importantly, the people making the decision did not fully understand how critical the maneuver had become, so the mission continued according to the original timeline. Minutes later, Mars Climate Orbiter flew into the atmosphere at an altitude it was never designed to survive. TCM-5 was not a guaranteed rescue, but the investigation concluded that it might have saved the spacecraft. The emergency option existed on paper. The organization had simply not prepared itself to use it. The spacecraft is often described as a $125 million loss. That figure refers roughly to the spacecraft itself. NASA training material placed the total mission cost at approximately $327.6 million. about 193 million for development, 91.7 million for launch, and 42.8 million for operations. But the scientific costs went beyond money. The orbiter never studied Martian weather. It never mapped the movement of dust and water vapor, and it never served as the planned communications relay for the polar lander. The navigation software was corrected for the lander, which reached Mars on the proper trajectory. Unfortunately, that mission was later lost during descent because of an unrelated failure. 2 Mars missions had disappeared within a few months. NASA responded with investigations, management reviews, and changes to its engineering practices. The reports called for stronger verification of software interfaces, independent reviews of mission-critical systems, better staffing, clearer responsibility, and culture in which concerns could be escalated until they were resolved. The easiest version of this story is that NASA lost the spacecraft because Americans refused to use the metric system. It is funny, memorable, and incomplete. The conversion error was real, but one incorrect unit should not have been capable of destroying an entire mission. The software should have been checked against its interface specification. The unexpected trajectory should have triggered a formal investigation. The navigation team should have had enough people and enough knowledge of the spacecraft, and the emergency maneuver should have been prepared before it was urgently needed. Human beings will always make mistakes. A reliable system assumes that they will. It uses independent checks, clear interfaces, realistic tests, and communication procedures to stop one error from becoming a catastrophe. Mars Climate Orbiter was not destroyed by one careless engineer. It was destroyed when a simple mistake passed through every layer that was supposed to catch it. And that is the pattern behind many of history's most expensive failures.